Today is March 19th, 2012. This is AP Statistics at Berkeley High School, and this is the finishing up of the 12-2 lecture having to do with transforming data into a linear pattern. Here's the idea that Moore, one of the co-founders of Intel, put forth back in 1965, the year in which I was born. And that is, every 18 months, technology increases so much that the number of transistors found on a computer chip doubles. That was his conjecture in 1965. We have data from 1971 to 2010 having to do with the number of transistors on a CPU. Now, we started last time by saying not all quantitative versus quantitative data is linear. This pattern, if you look at the red dots going there and then also in the very, very steep incline, that's not linear. We are going to ask the question, if it's not linear, could it be exponential? Exponential growth happens when we have some sort of multiplying factor over some set period of time. We talked about bacteria last time. Double every 4 hours kinds of things. Could this be exponential growth? Well, there's one way to find out, and that is to transform the data. And if we transform it in a certain way and we end up getting a linear pattern, then we'll say, indeed, we seem to have exponential growth. So let's start by getting this data into your calculator. Everyone get your calculator out, please. And then let me, I'm gonna make a quick adjustment in this data for you because there is some tricks to doing this easily. The numbers that we work with will work better if the X numbers are actually small. So when you start putting this data in, like for example for date, you're going to put the date numbers in L1, but I don't want you to put 1971 in. I want you to put 1. And I don't want you to put 1972 in. I want you to put in 2, 4, 8. 1982, I want you to put in 12. So we're always going to be years after 1970. So 12, 15, 19, 23, 27, 29, 30, 33, 34, 36, 38, and then 40. I think I can zoom in on this just to make it maybe a little bit easier for you to read. Let me scoot this up too. There you go. Can you read that a little bit better now? Okay. So go ahead and do that. And then the number of transistors, I want you to put that in L2. By the way, you may find it also easier to do a little bit more cheating when these numbers get really big, like in the millions. Remember, a million is 10 to the 6th. So when you get to like 1,180,000, you may want to enter that as 1.18. Say 1.18 times 10 to the 6th, which on your calculator ends up being 1.18 E6. So you may find it a little bit easier to enter in those big numbers and not get lost with how many, did you put enough zeros in there? get this data in my calculator as well. Yes? Sure. Okay. Okay, I got my data in. Anyone need more time getting data in? All right. So I've got my data in. You've got your data in. Let's go through that procedure one more time. How do we prove that this is not linear? We've already looked at the scatter plot. What's the other place that we look at to show data? This combination of data is not linear. I think it's got to be the residual plot. But in order to do the residual plot, we have to do a linear regression first. So let me remind us where that comes from. Second quit. Residual plot is under stat, calc, and we use option number 8. And we're going to use L1, comma L2. So there's our regression. If we were to do the residual plot, we'll go second stat plot. Turn plot 1 on. We still want an XY plot or a scatter plot. And we want L1, but we don't want it versus L2. We want it versus residual, which is 7 on my list. And then we can do a zoom 9. And the question we ask of this plot is, do we see a pattern?
Then you enter your data wrong. No. Oh, that's fine.
Does it look okay? Jacobs, you said it?
No, it looks the same as mine.
Okay, so either we did it equally wrong,
Yeah.
or Paul's right.
Equally wrong.
All right, so we see a pattern in the residual plot. We say that's evidence against the claim that the data is linear. All right? So what's our next step in this process? Well, our next step is to say, well, if it's not linear, perhaps it's exponential. How do we find out whether it's exponential? Well, the procedure that we introduced last time was that we're going to take all the data in our y, in our response variable, and we're going to take the natural log of it. Because exponentiation, taking something to a power, is undone by taking a logarithm. Yeah?
Does it matter that you forgot 2 zeros on
You did enter your
4?
data wrong. You're skewing it.
We're so skewed. See, that was a joke. See, instead of using the word, I used the word skew. See? All right. Was it 2,500? And 5,000?
It's not.
Actually, probably what's going on is that because these numbers are so relatively low compared to everything else, it didn't show up very much.
I just have an eye for this stuff.
Okay. So I still think that the majority of the data, of course I can't see the residual plot until I do another linear regression. Let me do another linear regression. Let me zoom 9 for a, okay, it still looks about the same though, right? Yeah.
I just have an eye for that.
Okay. So let's let's transform the data. We're going to undo the exponentiation by using the natural log. So what we're going to do is we're going to take the natural log of everything in L2. So I start by getting my cursor up in the header of L3, say natural log of L2, and there's the natural log of everything that's in list 2. And now I'm going to ask, between list 1 and list 3, do we have a linear relationship? If we do, then we say that the relationship between L1 and L2 has to be an exponential relationship. Well, let's go ahead and let's do a scatter plot of L1 versus L3. Second stat plot. Still want a scatter plot. I want it L1 versus L3. And I'm going to do a zoom 9. Except, try it again. Zoom 9. I must have one really bad data plot. I think this one's got to be off.
Yeah, I think you put too many zeros on it.
Okay, let me see if I can see trace. Should be easy to find.
It's not. You put 180,000. Put too many zeros.
180,000. Oh, how do I do this? Stat.
180,000 is too big. 180,000 is not 1.18.
That's a million.
No, this is the 1,180,000.
Just scroll down.
But you guys do not have that same weirdness, right?
You skipped one.
Three.
Oh, yeah,
Three.
yeah.
L1.
Oh, okay. I screwed up one. There we go. So that should be 33.
Not sweet coding.
All right. So just for
I'm standing up because it's so good sweat.
just for completeness, then I'm going to go back and redo the regression. I'm going to go back and look at the residual plot. Zoom 9. So here's my residual plot now. Now does it match? That looks a little bit closer to yours. All right. Let me go back. And I'm going to need to... Oh, wait. The problem was in list 1. So my list 3 is just fine. Assuming I got all those data things in fine. So list 1 versus list 3 should be ready to go. So let me try that again. List 1 versus list 3. Second quit, zoom 9. All right. And then what say you about that? Does that look linear? Okay. So again, and your paper. This is the takeaway from this demonstration. If after taking your y data and taking the natural log of all your y data and mapping your x versus log y, if you get a linear pattern, the conclusion is that the relationship of the x data to the y data is exponential. if you see linear in x versus log y, it means that x and y have an exponential relationship. I guess the question now is, what is that exponential relationship? Well, let's go back to here and let's start exploring what that relationship would be. All right? Now, what they've done here is that they did the linear regression for the transform data, meaning they didn't say, give me the line of best fit for x versus y. They did, what is the line of best fit for x versus log y? We, of course, can do the same thing by saying, stats, calc, linreg is under 8, and we're going to do L1, comma, L3, x versus log y. We get an x and a y value. Sorry, not x and a y value. We get an a and a b value. So let me take you through the process of saying what the exponential relationship is. We have that the natural log of y is equal to 7.1839799702. And I hate to say it, but this particular procedure really gets messed up if you drop any digits. So where I could usually say, round to 3 digits, round to 4 digits, not on this particular exercise. So this number plus 0.3538374039 times x. So that's the linear relationship between x and log y. Now, from an algebraic standpoint, we're going to take both of these numbers, log of y and this whole big mess of things, to the e power. And when we do this, the e and the natural log y cancel out, and we're left with just y. Or I should say, y hat. And then over here, we get e to this number, and the funny thing about exponents, they actually act like a multiplication when you add them. We get e to the other number, the slope number, and again, because of a weirdness having to do with the properties of exponents, we can put that x right up there. Now, e to 7.18 blah 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 is not probably very meaningful to you. E to the power of 3538, that's probably not very meaningful to you. So let's change it to numbers that are meaningful. So I'm going to go and figure out what e to 7.18 is and e to 0.353 is, and let's see if we can make the numbers mean something. So I'm going to, if you have already written this down, I'm going to get rid of it now. And what I'm going to do is ask the calculator second, e to the x, and that long number that was stored in a, I didn't write it down, so I'm going to just grab it out of the calculator. 5 for statistics, over to EQ for regression equation, and there it is, option number 2. So e to the a is 1318. What meaning does that number have for you in the context of this problem? It is the number of transistors that would have been or predicted it for a chip in 1970, in year 0 of our data. Remember how we said 71 was year 1? This would have been the year 0 data. Okay, let's do it again. Let's do second e to the x, and this time I'm going to grab the b value. Again, that was under vars. Number 5 for statistics. Over to EQ because we're looking at regression equations, and then option number 3 for B. All right? This number is 1.42. What meaning does this have in the context of this problem? It means, are you ready? Every year there was about a 42% increase in the number of transistors on the CPUs. Now where am I getting 42%? I'm grabbing this portion of that answer. Okay? If that number would have been 1, then no matter how we change the x, we would just be multiplying by 1 and there would have been no change. If this number was less than 1, it would have represented an exponential decline, like a radioactive decay. But this number is bigger than 1, it's an increase, and that number is increasing by about 42% per year. So, that's the interpretation of what we've got. We started with a linear regression, and we were able to transform the data in order to get an exponential equation that models this data. Now, that's what the College Board wants you to know about exponential regression. They want you to think about it only in terms of switching it to linear and then transforming it back into an exponential equation. The people at Texas Instruments, on the other hand, had a different idea. Under stats, under calc, we have linreg, we've got quadreg, change it into a quadratic, cubic, quartic. Go down that list just a little bit further. There's one called xreg, exponential regression. Now, this isn't on the AP exam because the writers of the exam want you to only think about using linear regression. But essentially, exponential regression L1, L2 are regular normal data without any transformation. Does all of that in the background. Do those numbers look familiar? Well, how do those numbers come about? The calculator did exactly what we just did. It translated the Y data, it did a linear regression, and then translated it back into an exponential equation. Okay, so for AP use, what do you have to know? You got to know the long way. You have to know about this relationship of transformed data. But if you use this on the quiz in order to check your answer, who would know? Nobody. Everyone follow me?
Who would know on AP and AP? Nobody.
Well, you got to remember how slyly they word the questions, Jason. Remember, they're going to do things like saying, they're not going to say, what's the exponential equation? They're going to say, questions like, does the linearity of the transformed data confirm, you know how they word those questions. They're going to screw with you. And that's why I wanted to, you got to know both or you're not going to be able to answer those questions. We hate them. So you show them. You go get your 4. You go get your 5. You show them. All right?
Get that number again.
How did I get that number?
Yeah.
If you're paying attention,
Okay. What I did was I did exponential regression, L1 versus L2, where L2 is the non-transformed data. Again, we can compare that to doing linear regression with L1 versus L3, where L3 is the transformed data. All right? All right. So, there we go on that. So, we did all of that. We did that. Oh, what we forgot to do is this. One of the things that we forgot to do. We didn't confirm the linearity. We didn't confirm the linearity of the transformed data. We looked at it and it looked linear, but what we didn't do is we didn't look at the residual plot. Here's the residual plot. Let me zoom in on it so that you can see it better. Whenever we do a regression, we want to look at that. And what do you see? I see pattern there. It does. It does. Okay. And actually, there's actually a reason for that. One of the things that have happened is that computers, we've kind of gotten to the point where computers are just like fast enough. The 3 or 4-year-old computer that I'm working on here, it really didn't need to be much faster than it already was for me to do things like word processing or browsing the web or spreadsheets, watching The Daily Show. There used to be a time where computer speed was like, I can't do this because my computers just won't handle it. Now we find that the amount of computer power has gotten to the point where we're not worried so much about computer power, we're worried about other aspects. New iPad came out last week. How much faster was it? Answer? Not that much faster at all. They didn't do much to the chip. They added some graphics capabilities so it could handle it. But it wasn't a faster computer. The big thing was they're going to emphasize things like battery life, and I think it has a new, it's supported by the new cellular network, the LTE network, which means it can download things faster. Things that matter to you now more like connectivity speed as compared to CPU speed. So there's been a much less push in terms of pushing the CPUs faster. So indeed, there's some variance, and it shows up in the residual plot. But these residuals are also really, really small. 1 and positive 1. It's not off by much. And so therefore, even though this residual plot shows a pattern, the relationship has been pretty linear. All right. I believe that takes care of that. Let me go back to normal screen size. Let's go on. This is them undoing the data. Okay. And then again, they say, even though it shows a distinct pattern, it's okay. So that's undoing exponential to show linearity. And now we just have one more thing to do. And that's to look at power model. We started with this whole thing with looking at the power model. This is the one that we introduced when we looked at pizza last Friday. Okay? Here's the idea. Again, linear models for data isn't always the best model. Maybe it's exponential. Or maybe it's raising something to a power. Like the way we raised the diameter of the pizza to a power to sort of get something that was more like area. But what if we don't know what the appropriate power is? Can we transform the data? And in doing so, if we achieve some linearity, maybe we could prove it's a power model, and also in this procedure, find out what the right power is. Okay. So we say, I'm going to add a couple more things to the notes here. We say that if it's linear, then its y hat is equal to a plus bx. We said if it's exponential, its y hat is equal to a times b to the x. Well, the last one is that if it's a power model, its y hat is equal to a times x. They use p here, but I'm going to put b there. the relationship of radius to area of a circle. It's a power model, and the power is 2, for example. Well, how do we find A and B? How do we find the A and the B, which will allow us to say what equation models this, and how do we make predictions from it? Well, answer is we do some algebra again. Oh, you know what? On that previous slide, I forgot to tell you the shortcut. Well, I just want you to know that if we're looking for, what was this? B to the x. When you do the linear regression, the number A always comes from e to the A, where A was from the linear model. And that B is always e to the B, where that B is from the linear model. So you don't have to remember how to do the algebra. You just have to remember that trick. Do the linear model and then just take e to the, and you get those two values. Well, we're going to do some more algebra, but we're going to do it with the power model. I guess I'll write this in a different color so it stands out. Let's start with the power model. Y hat is equal to A x to the B. If I take the natural log of both sides of this model, I get the natural log of y hat, and there's a property of logs that say if you're multiplying these two things, you can actually break them down as an addition problem. And there's an additional property that says if I'm taking something to an exponent and taking the log of that, that can be written as b times the natural log of x. One teacher at Berkeley High calls it the bring it on down rule. Well, you know what this looks like? This looks like some variable is equal to some constant plus a constant times a variable. That looks like a linear model. Not of x and y, but of log x and log y. So let's see if we can figure out what's going to go on. To figure out whether it's exponential, we take the log of all the y values and see if x versus log y is linear. Maybe that doesn't work. Maybe we try taking the natural log of both the x's and the y's and see if it creates a linear model. If it does, then the power model is the appropriate model. Let's see if we can do that with some data. I think we have some data coming up. Let's see what else they have to say as well. Okay, there's them taking the natural log to both sides, just like I did. Oh, there's them saying log of y equal log a plus power of log x shows that it'll be linear. Okay, I said that too. Power p is the slope of the straight line. Well, that's nice. That means if we do the linear regression, all we have to look at the b value and we'll know what the power is. That's nice. So the model, again, describes a relationship between two variables, and we'll find it's a power model if both variables, after being transformed, produces a linear pattern. And then, of course, once we get the power model, now we can make predictions. Given an x, tell me what y is. Okay. Oh, here we go. Here's some data. Time to put it in. You're going to clear out all the data in your calculator. Clear out L1, L2, and L3, because we're going to need L1, L2, L3, and L4 to do this problem. Let's start by Magnifying this so you can get in. Everyone able to see that? So distance from sun, I would like that to be my x variable. Let's put it in L1. And period of revolution, let's put that in L2. Freeze the screen. So I can put it in my calculator as well. This is a nice small data set. Okay, everyone in? Okay. Unfreeze. Unmagnify for you. Oops, that was interesting. There we go. All right, so there's our data in L1 and L2. So let's just sort of run quickly through the gamut. Do we think it's linear? How do we do that really quickly? We graph it. Second stat plot. We're going to do L1 versus L2. Second quit. Zoom 9. Golly, it kind of looks linear. But what's the true test? You know, usually the word golly gets a laugh, or at least a chuckle, or snicker. That was pity. That was just pity. All right. So that's not, whether it looks linear here, the real proof is in the residual plot. So we need to go second quit. We need to do a regression, not a program. We need to do a regression number 8, L1, comma, L2. That gives us a residual list. We go back to the stat plot. So much easier on the new calculators. Can't wait till we start adopting them. Zoom 9. Okay, do we see a pattern? Clearly, we start up high, we go low, we end up high. There's clearly a pattern in the residual plot. We are not satisfied with the linear relationship, so we say maybe it's exponential. Let's pretend we do the exponential. It's not exponential. Let's propose that that's a power relationship. So, how are we going to show that it's a power relationship? We have to transform both data lists. So, in L3, I'm going to put in the natural log of all of the X data. Natural log of L1. There it is, all filled up. I want to do the same thing with my Y data. So I go in the header of L4, natural log of L2. So now L3 and L4 are filled with natural log of X and natural log of Y. And now I'm going to ask the same questions that we've done before. Are those two data sets linear? Let's find out. Second, stat plot. L3 versus L4. And zoom 9. I don't know, that looks pretty linear. Is that the real test? Let's try that one more time. If it looks linear, it must be linear, right? No. The real test is looking at the residual plot. So let's go ahead. Let's do a regression, stat, calc, 8, L3 versus L4. So we're doing the regression against the transformed data. Right? Let's then look at the residual plot. L3 versus resid. Second list resid. Enter zoom 9. Ooh. That looks patterned as well. No, because we have to do it against we've got to do it against the X data, which is in L3. I am not concerned about this pattern residual. Would you like to know why? Look at the size of this residual. 6.5 times 10 to the negative fourth. This residual is 0.0006. That's really close to being right in the prediction line. While this residual plot has a pattern, it's not, the deviation from prediction is really, really small. I am not concerned about this. Okay? So what do we have then? What we have is a relationship between the data. I'm going to do the regression one more time. Okay? What we have is an equation that says that the relationship between the data is that the natural log of y is equal to the natural log of a, which is 2.544 times 10 to the negative fourth, plus 1.49 times the natural log of x. Now, if we undo the natural logs on both sides, is that how that's going to work? I'm fading here. Let's see what the publisher has to say in this. Okay. So there's what they did. Okay, here's where they tried to do exponential, it didn't work. Here's where they did the natural log of both sides, and it turned out linear. And here are those two values down here that we got on our calculator. And I think the biggest point is that the real relationship is that it's going to be distance to the power of 1.499, or if you would guess that if mathematics is supposed to work out really nicely, it's probably supposed to be 1.5, or distance to the 3/2 power. That's the power that's going to describe the relationship between those variables. Now, I finished off the exponential stuff with saying, here's what the College Board expects of you. but here's what TI gives you for free. The calculator will actually find the power model for you. You just have to know where to look. Oh. Did I overshoot it? Okay. So that model can be done directly without doing any transformations, L1, L2. Totally untransformed data, and you can see that the model that it comes up with is x to the power of b, and b being that same number that we had before. Now, again, this is the two worlds. This is the practical world. If you really need to do this, it's there for you. If you want to check your answer, it's there for you. But the College Board has a different expectation for you in terms of dealing with this data. So I want you to be able to work in both sides. And I do believe that probably finishes it off. Okay. Oh, last part. Why do we get the models? So that we can predict the value. Given an x, you throw it in the model, you get a y hat out. So don't forget that the whole power of this is to be able to predict what would happen at some other value. All right. So you know what your schedule is for tomorrow. You got quiz tomorrow, review on Wednesday, and the half day Thursday, and the test on Friday. Any questions? You've been a very sleepy audience. Thank you very much.
Good night.